Swayam Prabha. Digital India. Educated India.
Lot of information you cannot get, like why a specific compound is colored, right? What happened to their magnetic properties? Because these are the things we are really interested in. So this is where crystal field theory comes in. Of course, it is based on the failure of the valence bond theory, or as that's how in the book you read, that where valence bond theory kind of fails, cannot explain further, and crystal field theory basically picks up. So of course we can just learn crystal field theory, but the problem is valence bond theory is so simple. I think nobody kind of, see, you cannot forget the history of something and just take the present. I mean, present is something different, not crystal field. It's something different, right? Which we may not be, or we will not be talking too much. So it's, present means temporarily present, okay. 100 years down the line, it would be explained in a completely different way, or more better way. Of course, crystal field theory has tremendous limitation as well, but we may not be talking about those. So as we progress, or as the chemistry understanding progressed, we will try to do. So what we are saying, that valence bond theory really cannot explain tetrahedral and square planar. Okay, when it is any distortion, what valence bond theory is discussing is an ideal situation kind of. Anything, bond elongation, shortening, these things cannot be explained by valence bond. In a moment you will see how the distortion is going on by crystal field theory. Color of complexes, of course you cannot have any idea about the color, what color the complex should be. I say a compound is this hybridization, or this many ligands are there, this there, that there. Crystal field theory can explain, however we didn't explain yet, but valence bond theory cannot explain those. Temperature dependence, why magnetic properties are dependent on temperature. If you increase the temperature, what happens? Whether magnetic susceptibility or the magnetic behavior goes up or goes down, or how it goes down, or how goes up. Those sort of things we will be discussing. Okay. Now, crystal field theory, first we have to look at the orbital. This is something you have to kind of have it within your mind very clear, what we are talking about, the atomic orbital, these orbitals. Mainly the 5d orbitals, right? We have 5d orbitals, how they are, and along the axis how they are, where they are. Now this is the z axis or g axis, whatever you want to call, okay? Now the dg2 orbital is going to be like this. The electron density is going to be over here and over there along the z axis. So axis you can think along this one. Let's say this is x axis, this is y axis, this is z axis. Okay? In 3-dimensional scenario, you can take this corner, any corner, one axis, another axis, my laser pointer failing. Any corner you can pick up, x, y, z, of course 90-degree angle. It may not be always true here. Now this is dz2 orbital, so along the z axis, this is dx2, y2 along the x and y axis, and this is, let's say, dyz, that means in between y and z. So if you look at here, if this is z axis, this is the electron density over here, and the lobes are here, and below this one there is lobe. Okay? If it is x and y axis, then dx2, y2 will be along these x and y axis. Along, just right on top of those axes. Right on top of the z axis is dz2, right on top of x and y, both plus and minus direction, is going to be your dx2, y2. And dxy will be in between. Dxy, where is dxy? Dxy, see, this is, let's say, x axis or whatever, y axis, x and y, as you see, these are right on top of the axis. In between x and y axis is dxy. Similarly, in between y and z is going to be dyz. So this is z axis, center, the lobes are here. this is dz. Now, if you look and say that this is, let's say, x and this is y, dx2 y2 is going to be here, right? So, and dxy is going to be, so this is y axis, this is x axis, right on top of y axis, sorry, we'll come to that. So it is going to be like that. Okay? Now you have to, I'm sure you have seen it before, you have to be really, really clear about their positioning. I think we'll come to that. Let me show you where they are. Over here. No, we'll come back in a moment. Let me tell you. So what crystal field theory assumptions are, it's very simply, these are electrostatic interaction. It's a metal center is a cation, ligand is an anion, most often, so it's a cation-anion interaction or electrostatic interaction, ion-ion interaction or ion-dipole interaction. Previously, we are thinking just about the covalent interaction, right? Now, if you are thinking, so metal has electrons. If you are bringing ligand has electrons. So these ligand and electrons and metal electrons are going to repel each other. They are going to, they are electrons, same charge, right? Although metal is positive, ligand is negative, let's say, or neutral, or whatever it is. But if you bring them together, those electrons of the ligand and electrons of the metal, they are going to repel each other. So thereby, the energy of the total system going to be increased. If d level energies are, for example, over here, if you bring the ligand from the equal distance or from the all distance or all direction equally, then also the energy of the d orbitals will go up. It's a spherical, let's say, cricket ball. You are going to put the pressure on cricket ball from all directions. Cricket ball is going to be destabilized. Well, in this case, ligand approaching ligand is going to make cricket ball destabilized. Okay. Now, this is under ideal situation where all the ligands, let's say, are coming from every distances or every directions, all the distance, all the directions. Now, in reality, what you have seen is ligands are not there from every directions. It is specific. Ligand is here, 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 and here. Only few directions. This is the direction for z axis. Let's say this is the z axis. This is the, let's say, whatever, y axis. This is x axis. Right. So ligands are going to approach the metal center only from a specific direction, not from here. It's just along this direction, not from here, not from here, not from there. It's a specific direction. Now, these are the directions where the metal orbitals are. There you have dz2, there you have dxy. This is the one where you have dxy. So, eventually what you will see is, I'll show you, since ligands are coming from this direction directly, those orbitals dz2 and dx2 y2 orbitals are going to be repelled very much, means they are going to be unstable, they are going to be high in energy. So over here 5d orbitals are there. Since ligands are coming specifically from z or towards z axis, y and x axis, any orbital that is facing those axes directly, they are going to find the consequences. That means they are going to have the energy increased, their energy will be increased. Any other orbital, for example dxy, which is over here in the middle, they are going to be perturbed, but not too much. In reality, with respect to this one, they are going to be stabilized, because this is the total stabilization, With respect to that, something is going to be destabilized, something is going to be stabilized. Okay. Now let's look back. All the orbital, if you look back one more time very carefully, this is the GZ2. Anyone has anything to say? Please speak out. Now DZ2 orbital, DX2 Y2 orbital, and you can see all these orbitals. Okay. Right now also, if it is not clear, you look back at the note, I am sure it will be very, very clear. The pictures are very clean. Now, as we are saying that plus and minus attraction, electrostatic attraction will be there. Now, two of these orbitals, which is dx2 y2 and dg2 or dz2, these are the orbital, let us say all these orbitals are there. These are the ones which will be facing the ligand directly, like this. So, ligands will be coming directly from two different angles or from two different directions for dz2. So, dz square orbital will be high in energy, right. It was previously, it was all of them are same and having same energy or so called degeneracy. 5 d orbital were degenerate, that is so far you have mostly learned. Of course, you may have learned this one as well, but since you see that there is a discrimination, there is a preferential attack, you are going to get it destabilized because they are going to interact directly. Now, if you look at the dx2 y2, this is the dx2 y2 orbital, and 4 of the ligands are coming from these directions exactly. Of course, this is going to be also destabilized. So, what you have learned so far is dg2 and dx2 y2 are going to be destabilized. But if you are looking at, let us say this is dxz orbital, okay, x axis and z axis. dxz orbital and the ligands are approaching right actually from the middle, not directly towards these lobes. So, their energy will not be overall destabilized because we have already destabilized by bringing the ligand. Comparatively, they are going to be stabilized. That is how the ligands are coming, right. Sorry. That is how they are coming in. So, they are not fitting the bill right on top of each other, they are just squeezing in, not head on collision. Now, so dxz will be stabilized, dxy, dyz is the same scenario, it is just different axis. So, overall we see that it is split into like this, 2 of them getting destabilized, 3 of them getting stabilized. Stabilized means stabilized with respect to where it started, not in the free ion over here. This is a free metal ion. With respect to free metal ion, when you have a metal complex formation, it is all the d orbitals are going to be net destabilization will be there, their energy is going to be high. With respect to this, some of them will be destabilized, some of them will be stabilized, but the net destabilization is going to be this much. If you have a free metal ion, it is stable. The moment you put ligand in it, it is going to be unstable or destabilized. With respect to that destabilization, okay, so that is how it is going to be. But with respect to free metal ion, of course, they are destabilized. Okay. Now, this is what is octahedral field is all about. You see octahedral complex, 6 ligands are there surrounding the metal center, 5 d orbitals getting destabilized and further splitted. This is no longer degenerate of the same energy, right. Now, this is also another way to look at it, 2 ligands and these black balls are ligands and how they are coming, and all the d orbitals are superimposed over here. You can see which are facing what. Okay. Now, this is for octahedral field, this is called EG orbital, and this is T2G orbital, 3 of them. So, EG is dx2y2, dz2, and T2G is dyz, dxz, dxy. Okay. So, 3 of them and 2 of them. Now, the extent to which with respect, this is called barycenter, where the 0 is. Okay. With respect to that, the destabilization will be the same amount compared to the stabilization. Why it seems like unsymmetrical? Because there are 3 orbitals, so 6 electrons can be filled. 6 electron versus 4 electrons. So 4 times destabilization and 6 times stabilization. So there is a factor. This distance from the barycenter, this distance is 0.6, this is 0.4. From the middle, this is 0.6 and 0.4. So from here, this is going to be 0.6, this is going to be 0.4. Okay, I should have stabilized, I should have switched off this one. 0.6, 0.4, okay? We'll come to that again. Now, some more informations are given which you can read very clearly. I will not dwell too much on that. Stabilized one, destabilized one. This is also another way of looking at this, the same thing, exactly same thing. You may not be able to see it clearly from here, but in slide it will be clear. dz2, dx2, y2 and the 2 orbitals and 3 different orbitals in the compound form or in how they interact. Okay? Further, it is much better. I think this is the last slide hopefully on that. You see dz square and dx2, y2, dzx, dyz, dxy. Same thing, how the ligand is coming. See, when you take the printout of these things, if you take the same printout, I don't mind, but the information is not different. But once you are seeing in the computer, for example, you will be able to see it clearly what exactly we try to say. That will give you a crystal clear picture, hopefully, what's going on in here. So once again, I will take the break in a moment. This is the 3,5 of the total distance is called delta 0 or 10 dq. This is going to be your 6 dq, this is 4 dq. Or so to speak, 3,5 delta 0, 2,5 delta 0. This is something you need to remember. The total is called 10 dq, 4 dq and 6 dq. 0.4 and 0.6, 4 dq, 6 dq. Okay? If it is delta 0, you are saying this is going to be 0.4 delta 0, this is going to be 0.6 delta 0. And these are the EG, T2G we will be calling. The difference between them is delta 0, 10 dq, so on and so forth. Anyway, so let's continue over here. What we see, this is the total 10 dq we are saying. What is dq? It will be clear soon enough. Or this is the delta 0, the distance between these T2G and EG, or the energy difference between these two. Some of them are destabilized, some of them are stabilized. Let's take some little bit more practical example. You have a titanium hexa-aqua complex with 3 plus, scandium titanium, okay. It's D2S2, it is going to be D1 then after 3 plus, so 3D1. So that means no longer we will be saying it 3D1, we are going to say it T2G1, EG0, because if you see the filling up of the electron, now it's going to happen the one which is stabilized first and then either over here or back to here. So the filling of electrons we are trying to see, no longer will be calling it D1. It has to be defined as T2G what, EG what. Let's say T2G5, EG0, T2G3, EG2, T2G4, EG2 or T2G6. So how we are going to do that? This is what we are going to discuss. So in other words, whether all the, let's say you have 6 electrons. 6 electrons, if you are having, each of them are 1 orbital. Therefore, technically you can have 6 of them over here, or 3 of them over here, 2 of them over here, and another over here. 4 plus 2, you can say 6 plus 0, or whatever other permutation combination you want to have. What order these d orbitals will be filled, that is what we are going to discuss. The answer to that question is very simply, it will depend on the ligand. That is why it is also called ligand field stabilization energy. Ligand, if it is a strong ligand, What is a strong ligand? Let's say, I'll come back to that again. If it is a, let's say, cyanide is a strong ligand. Okay. Aqua, water, let's say, for example, usually a weaker ligand. Or, it's all relative again. There is a spectrochemical series we will bring. Okay. That will tell what is strong ligand, what is weak ligand. Fluoride may be a weak ligand. Okay. So chloride may be weak ligand. CO may be a strong ligand. Okay. So on. So depending on the difference this energy is having, like how much difference is there between T2G and EG, it is this much or that much. If it is this much difference, then electrons will be occupied all T2G and EG, because you know that Hund's maximum principle, that spin has to be maximum and so on. But if it is this one, that Hund's rule may not be applicable here, because it is very big. So putting electron in this orbital, EG orbital, is going to cost you too much of energy. Of course, another problem is the pairing. For if you want to pair up, pairing energy is also there. If you want to pair up over here, some energy you have to give, whether pairing energy is high or the distance or the energy difference between these T2G, EG is high. That you need to kind of know. You don't need to memorize, we are going to tell you what is the scenario. Okay? So we need to know what is the ligand, what usually is the pairing energy, what is the oxidation state of the metal. That also varies. Higher the oxidation state, you will see the splitting will be high. This T2G, EG gap will be high. 3D to 5D gap will be increasing. 2 plus to 5 plus gap will be increasing. Therefore, if the gap is increasing, pairing become easy, because it cannot go too much if it is gap is too much. If gap is low, then pairing will not occur. It will be both in T2G and EG. If this is EG, this is T2G. Okay, that's what we are going to see now. I'm kind of summarized. Over here, it is going to be T2G1, EG0. Now everything you have to explain, or you have to write in this format. Why we see purple color in this titanium hexa aqua complex? Why do we see purple color? It's like this. The UVB's maximum, the absorption is going to be this 20300 or 20300 wave number. So that is actually the gap between the T2G and EG will show. So let's say this is your T2G electron, and you put the energy, the light, it is going to convert from T2G level to EG level, and that is where you see in terms it comes out the absorption energy, where it absorbs. That means how much energy you have given to bring, let's say, T2G electron, one electron from here to here. That is what nothing but you see as absorption. The peak you see, or you have a metal complex, you shine light, you want to see the electronic transition from one level to other. It could be, let's say, sometime T2G, T2G, or it could be usually for one to see, you have to have T2G to EG conversion. From T2G orbital, any of them, because they are degenerate, to over here. That's the energy you need, and that is going to be your absorption energy. And depending on that, how much energy you absorb, as we say why the color, different color comes, how much energy is required, based on that, or what wave number is required, based on that, you will be able to see the color. So you give them white light, simple light, we end up seeing some color based on what is being absorbed and what is being emitted, or indirectly what is being emitted. So for T2, this titanium hexa aqua complex, we see that this is the UVB's absorption. This is nothing but this transition from T2G to EG level, and that is how the peak is coming. Okay, that's the absorption that is happening for transferring T2G electron to EG electron. Of course, there could be multiple transition, there could be multiple, if it is a simple electron system, one electron system. If you have 2 electron systems, 3 electron, 4 electron, 5 electron and so on, and based on the electronic configuration, you can have multiple transition. Therefore, your peak could be like 3-4 peaks, or I mean your spectrum could be having 3-4 peaks, or different region, different things can happen. So simply speaking, some sort of transition has to occur. In d orbital itself, 5 of them are degenerate. You are not going to explain. That's why you cannot explain color by by valence bond theory. But crystal field theory gives you an idea of where the origin of the color is. This is nothing but transition of one sublevel to another one, right? So this is where crystal field theory becomes superior compared to your valence bond theory. Valence bond theory, what you have done, D2 sp3 or sp3 d2, whatever, sp3 and so on. There you cannot explain where the color is coming from. Okay, enough. Now, of course, as I said, there are scenarios where you can have more than one electrons, right? So d1 to d3, so of course Hund's rule will be promoted. Now for 4 electrons, you can have T2G4 Eg0, T2G can have total up to 6 electron, or you can have T2G3 Eg1. 3 of them are going to be filled out. After filling out, the 4th one will be the Eg1, Eg, right? Now I'll come with that with more pictorial diagram. I think I'll skip that. Now this is what it is. So T2G orbital 1 electron, T2G orbital 2 electrons, T2G orbital 3 electron. There is no story of Eg because Eg is high in energy. Why it will go to high in energy? After D3, then you have dilemma. Then you have problem. Whether you send it to Eg or you pair it up with T2G. So there are 2 scenarios. High spin complex will have T2G3, Eg1, D4, option 1. Option 2 will be T2G4, Eg0. This is T2G, this is Eg, Eg over here, nothing in there. So you have low spin complex. This is high spin complex because 4 unpaired spins are there. Here you have 2 unpaired spin. So up to D1, D2, D3, you do not have to worry at all. You just put T2G1, T2G2, T2G3. After that, whether it is T2G4 Eg0, T2G4 Eg0 or T2G3 Eg1, which one is going to be predominant or which was going to be happening? That will be determined by ligand, metal, which metal it is, what d orbital they are having, what is their oxidation state. All these factors will put together will determine whether it is going to be a high spin complex or low spin complex. It's not complicated at all, just go through simply. I'll try to explain when, what you can expect. You don't have to remember again, you don't have to remember what will be the delta 0 and what will happen. That sort of memorization is not required. Okay. So in other words, if delta 0 or that 10 dq value we were talking, difference between T2G and Eg, if this is small, then you will see T2G3 Eg. If that difference is small, the spin will try to be maximum, or electronic spin will be maximum. So T2G3 Eg1 will be happening if delta 0 is small. For this to happen, T2G4 to happen, you have to pair these 2 electrons, right? That means you are dealing with pairing energy. If pairing energy is favored, if pairing energy is less compared to this delta 0, then you are going to have this low spin configuration. Okay, now of course lot of things I have given, written the same thing again and again written, but essentially once it is clear to you, you do not have to read this slide too much. Okay, I think we have explained already. Now I will just give you a phenomenon. So what we have said, up to D3 you do not have to worry, it is going to be T2G1, T2G2, T2G3. After D4 you have to decide. That again, let's say at D8 you do not have to worry, it is going to be T2G6 Eg2, 1, 2, 3, 4, 5, 6, 7, 8, whatever way you want to fill out, D8, D9, D10, you don't have to worry. it is going to be only one configuration possible, because your goal is to minimize the energy without compromising the spin. Of course, Hund's rule says the spin should be maximum, right? You try to do that, but while you are trying to do that, you have to also mind the gap, distance between T2G, EG, whether it's going to be unpaired spin or paired spin. After filling T2G, you have to up from 4, 5, 6, really the one cases where, and 7 as well, 4, 5, 6, 7, you have to worry about whether it's going to be high spin or low spin. Up to 3, it is going to be always high spin. There is no low spin scenario, almost, right? And after 8, 9, 10, it is always one configuration. 4, 5, 6, 7, it is going to be high spin or low spin. That's what you are going to use. High spin means spin is maximum. Low spin is minimized with the given situation. Okay. Now, something like these complexes. If you see some EG complex, like very soothing for the eyes, those are going to be high spin. Like iron aqua. Very EG complex, looks like water molecule, iron is there, 2 plus, mind you. EG complex. The difficult complex could be 3 plus, means which is more higher charge. Now, this is going to be high spin over here, because the delta 0 you see is this much, pairing energy is high. Pairing energy high means you are not going to get it paired. You are going to have the unpaired spin, right? Now, iron hexacyanide. We are all talking about octahedral complex. Don't forget that. 6 ligands are there. We didn't talk about tetrahedral as of yet. So 6 of them, this is going to be a strong ligand. Cyanide is a strong ligand. That means the gap between T2G and EG is very, very high. Okay? This will be D6, right? So those 6 electrons will be T2G6, not T2G4, EG2. I think some of you are having little bit dizziness. Let's see. Try to explain in the board. What we are having, let's say D6, this is T2G3, 3 of T2G and 2 of EG. You can have this as one scenario, right? Other scenario is nothing here, all paired up, right? So this is T2G4, EG2, this is a high spin situation. That is what is happening in iron hexaaqua complex 2 plus. Now iron cyanide 6, FeCN6, hexacyanide, okay, 4 minus. Now you have D6 total electron, right? Now, of course, how it is iron 2 plus, this is also iron 2 plus. Both of them are iron 2 plus. Iron 2 plus, that's why it is 2 plus. Iron 2 plus 6 minus, that's why it is 4 minus outside, right? Both of them are D6 electronic configuration. Only thing that is differing is the ligand. Metal is in the same oxidation state, hexa coordinated, ligands are different. What you are seeing here is the distribution of electrons are different. The first one will have this electronic distribution, second one is going to have this electronic distribution, because let's say, so to speak, the difference between these two guys is high. This difference is very large. If you look at this delta 0 or 10 dq is this much, pairing energy is less. So thereby it will pair up very easily. Electron cannot go and jump over there. In this case, the pairing energy is high, but delta 0 is small, so it is going to follow your Hund's rule, okay? Or I mean, of course, it is always following Hund's rule. Sometimes there is no option. Okay, when there is no option, you are going to end up getting that configuration. This is usually speaking, most of the cases I think high spin will be preferred. Of course, most of the cases is a wrong statement, but It's a ligand dependent, metal dependent, but lot of things that we see in in the regular books, usual books, those are going to be high spin species. Unless it is high oxidation state of the metal and strong ligand, it's not going to be low spin. If it is high oxidation state, let's say iron 4 plus or some high oxidation state and ligand is strong ligand, then you are going to see low spin because the T2G and EG splitting is going to be high. Okay. Now next one, cobalt F6. Cobalt is here 3 plus, 6 of the fluoride, 3 minus total, D7 configuration. Cobalt is D7S2, iron cobalt, yeah. And then if it is iron cobalt nickel, D7S2, it is 3 plus, right? I think something is wrong there. Is it not? It should be D6, right? Okay, let's assume that this is D7, but these charges are wrong. Okay, cobalt is D7S2, so 9 electrons. If 3 are taken, so 2 are taken, then it is. Let's say this is going to be your 4 minus. Okay, the charge is wrong here. I don't know how come. So anyway, it's a D7 system, both of them are D7 system. Ignore the charge, just take my word. Ignore the charge. D7 system, D7 system, one is high spin, another is low spin. It's also to tell you, sometime you see the ammonia complex is going to be low spin, sometime it is high spin. Again, that depends on the metal center. I'll give you a summary. Okay, let me give you the summary. The delta 0 will be increasing in this order, 3D, 4D, 5D. 5D will be highest. Higher oxidation state will give you the higher delta 0. Now, over here you see with the chromium, chloride, aqua, ammonium, cyanide, the energy between T2G and EG, how they are differing. So you can say that this is a weaker ligand, this is little bit stronger, this is more stronger, this is the strongest in this series. So the difference between T2G and EG can tell you what is the strength of these ligands are. Okay? Depending, keeping the metal constant, oxidation state constant, you are changing ligand and you are saying that the splitting you are varying. So that will indirectly measure the strength of the ligand. Okay? Now over here you are keeping ligand constant, oxidation state constant, everything constant, but you are changing the metal center. Cobalt, rhodium, iridium. In the periodic table look at. Now you see how they are increasing. So the overall trend is 3D splitting will be least, then 4D, then 5D. Metal oxidation state will also vary. That is also over here. All these things summarized together, I'll tell you what is summarized to. This is what it summarized to. Okay? You can take a series of compound, just vary one thing, either ligand you vary or metal you vary. You keep on doing, you come to a conclusion that 5D will have higher splitting than 4D and 3D, and higher oxidation state will have higher splitting. Now there is something called electrochemical series. This is what is electrochemical series. This is the strongest ligand, then this one, then that. So the idea here is, if you have high oxidation state and strong ligand, you are definitely going to get a low spin complex. High oxidation state, splitting will be high, strong ligand, splitting will be high. So low spin complex means the splitting is going to be high, so the electron cannot jump to the EG, so it's going to be low spin. Spin will be minimized, it will stay in T2G. Now you can think about the different permutation combination. That's why it is not that very easy to say what is going to happen unless you give the exact combination. So the strong field ligand, they will tend to give you high delta G or delta 0, right? T2G EG separation will be high, therefore it will give you a low spin complex. Strong field ligand will tend to give you a low spin complex, but that does not mean that any metal you take you will always get low spin with, let us say, cyano or any of the alkyl or nitrite. You have to, of course, you also have learned that 5D will have more splitting than 4D and 3D. Higher oxidation state will have more splitting than lower oxidation state. So it is a combination of all these three factors where the ligand is in terms of spectrochemical series, not spectrochemical series. Where the ligand is, whether it is strong field, this is the strong field, these are the weak field. Where it is, and then what is the oxidation state of the metal, and what orbital metal is having. Okay? If everything strong, then you are going to get high splitting, low spin. If it is very small, you are invariably going to get high spin. Okay? You just read through little bit, first the slide, look at the slide, and then go through the books. I hope it will be clear. Okay? Now it is summarized in here once again, and this is the summarize for this ligand. So overall, after having this, you should be able to calculate the crystal field stabilization energy. How much with respect to the 0, how much stabilized or destabilized it is. So over here, each of the electron over here, I said it is 4 dq, right? 4 dq, and this is 6 dq. So you can see that 3 of them, let's say if you have 3 of them, 4, this is 4 dq, 4 times 3 will be 12, and 2 times 6 will be, this is 6 dq. This is also 12. So 3 over here, 2 over here, net stabilization, net destabilization will be 0. Nothing is left. 3 over here, 2 over here, symmetrically filled. 4 times 3, 2 times 6. Now the moment you put it here, 1 electron, the stabilization energy, crystal field stabilization energy, that is what called crystal field stabilization energy. 3 and 2 is 0. In this case, it will be 4 dq. Of course, dq has a value different for different compound, as we have seen in the dq is changing. But we don't memorize those data, just say that it is 4 dq. 4 dq could be 500 wave number, 4 dq could be 2000 wave number. But this is 4 dq. That dq depends on what is the extent of splitting, how much, how far it is splitted. Okay. Now this is having 4 dq stabilization, this configuration. 3 and 2 cancels out, just 4 dq left. If you have one more electron over here, 3, 2 cancel out, 8 dq, right? One more, 12 dq. 3, so you can calculate also, 4 times 6 is going to be 24, and 2 times 6. This is stabilization, this is destabilization, 12. So it is also 12 dq, right? Other way to say it, 2 and 3 is cancelling, completely 0, 1, 2, 3, 4 times 3, 12. So this is 4 dq, this is 6 dq. Over here, it is each of them are 4, nothing is over there, 4 times 6, minus 24 dq. Stabilization means usually we put minus, okay? That much it is stabilized. So you can, these are number that's called crystal field stabilization energy. So you can of course this calculate based on this. It's 4 or 0.4. I mean, if you are saying delta 0, then it is 0.4 and 0.6. If we are calling 10 dq, this is 6 dq and 4 dq. Right. It's very simple math you should be able to do. For example, over here, case 1, you have low spin case, that means the splitting is high. Low spin case, so the stabilization is going to be 5 times 4. 5 electrons, 4 dQe each, or 0.4 delta 0 each. So it's going to be 20 dQ. Over here it is going to be 0. Right? So this is again, it's called crystal field stabilization energy. Due to this crystal field theory, the splitting comes, and thereby what is the stabilization energy? You look back to the valence bond theory, you don't talk about any stabilization. You cannot talk. All d orbitals are degenerate, means same energy. dxy, dxz, dx, whatever, are the same energy. Here you have splitted them. Therefore, stability and instability are coming into the picture. That's what is crystal field theory for octahedral.